So the next thing that I have in this chapter 8, 9, and 10 unit is something that does not really belong with any other thing that we've done. Maybe we could have put it with the thermochemistry, but I didn't. And so this is a good time to just to introduce it. You will have questions about this, and there's lots of questions about this on the AP exam as well. In fact, when I get talking about this, you're going to remember when you studied for the first review quiz, there was questions that related to this. I only had one person asking me questions, which was kind of surprising to me, because I know more than one person did that packet to review for the quiz. But when you dissolve a solute, dissolving always means that the solute it goes into the solvent, and the solute particles get broken apart from each other, and the two mix together. There are 3 steps. Each of them, we need to pay attention to what happens with delta H in each of those steps. The first step, and it's not necessarily in this order, but one of the steps, I should say, is the solute has to break apart. If the solute doesn't break apart, the silly thing doesn't dissolve. It just sits there at the bottom, or it floats on the top. But yeah, in order to dissolve, the solute must be broken apart. And that means bonds must break. So that delta H1 is always a positive value. Now the second delta H is a little bit strange. Not only does the solute break apart, but the solvent actually has to spread out or break apart and make room for the solute. This is the part that I wondered if you would remember. There was one, I know at least one question that showed it showed a particle drawing. Like if that is the solvent, after the two interact, it's more like this. You remember that review question? Yeah, that was in there. This topic is what that question was getting at. So yeah, the water itself has to somewhat break apart and make room for the solute to come into it. And that, because we're breaking water molecules apart even a little bit, that requires energy. So delta H1 and delta H2 are always positive. The stuff is breaking apart. But then you get to delta H3, in which that's what's happening where the solvent and solute start to attract or interact with each other. And it's like bonds are being formed. They may only be intermolecular attractions, but there are bonds. Now I say usually negative because there are some exceptions to that. Sometimes the delta H is positive with that interaction. And sometimes it'll actually dissolve even though we don't think it should. Some things will dissolve. For instance, carbon dioxide. Carbon dioxide dissolving in water is not something you would expect to happen because water is very polar and CO2 is quite nonpolar. But still, carbon dioxide will dissolve. And water doesn't really even like carbon dioxide that much. The two don't have much compatibility. But CO2 still dissolves, and that's what gives the fizz and pop. So we have 3 delta H's. When you add them together, you get an overall delta H of the solution. The process of dissolving, the scientific word, there's several scientific words for it, but commonly we use the word solvation. The process of dissolving, including those 3 steps, we call solvation. But people also call it dissolution, too, especially for ionic compounds with them breaking apart. All right, we good with that? So we have this, this overall delta H And here's what we do with it. You know that for a system or a process to be spontaneous, it has to have a negative delta G. So we're looking at the delta H, and we also know this. The delta H equals delta G equals delta H minus T delta S. So looking at this term right here, how does that affect delta G overall? We know that when delta H is negative, that's favorable. What is favorable for delta S? Negative or positive? Positive is favorable. Yeah, you got to know that. And most of you do. The scores on the review quiz were great. You did very well on the review quiz. The part that I checked, at least. I got through the multiple choice part, and then the other part I didn't. What was that reaction? Okay. When something dissolves, what would you say about its entropy, or the entropy of the system? Is it going up or down? Yeah, it would be going up. Things are becoming more disordered or messy as they mix together and break apart. So you got two things breaking apart and then mixing together. So it's very much more entropy from dissolving than before they dissolve. So anyway, the delta S of dissolving is always favorable. The delta H might not be favorable, though. It depends on what 1, 2, and 3 are. So if delta H is negative, then you got that being negative and that being positive. Delta G will definitely be negative, and your solute will definitely dissolve. If delta H is positive, then that is non-favorable with that being favorable. So that's why I say the solution probably won't dissolve. It depends on how big delta H is. That depends on what your other numbers in that are. Because I got this last bullet point too. If delta H is small, I mean if delta H is negative anyway, it's going to dissolve. But even if it's a small positive number, it's probably still going to be spontaneous because it'll still be dominated by the entropy change. Now, on the next slide, I just have a couple other terms that go with this. Remember, delta H1 is the solute breaking apart. So if the solute is an ionic compound, delta H1 requires that ionic compound to get broken apart, for those ionic bonds to break. We decided that the energy involved in ions getting together is called lattice energy. Remember we talked about that at the beginning of the hour, the lattice energy? If you have that ionic compound already made and you want to break it apart, would you agree that the amount of energy is the lattice energy, but is the opposite direction? So lattice energy is always negative because when ions come together, they always give off energy when they make a bond. So if you're trying to break an ionic compound apart, that means the lattice energy is you're going to use the same amount of energy, but it's going to be the opposite. So delta H1 is the opposite of lattice energy. And I would just mathematically show it like this. Now, negative delta HLE. That's delta H1. Then there's another expression, I guess, where you got the expansion of the solvent and the interaction. We call those added together the enthalpy or the heat of hydration. Now, sometimes heat of hydration actually shows up in a question. I've got one, a sample question on the next slide where you'll see enthalpy of hydration. All right, can I change the slide? Check this one. You don't have to write the question out. Just see what you make of this one. This is in the book. What's the delta H? So we know that. We're given the lattice energy is negative 686. So didn't we agree we turn that around and take the negative of it? That takes care of that one. Then the delta H2 and delta H3 together make up the enthalpy of hydration, which is given to us. That's it. Negative 8. So delta H is negative 8 kilojoules per mole of sodium iodide. So we have a favorable delta H. It's not big, but it's still negative, so it's favorable. And the delta S is favorable. So this for sure, and I know from experience that sodium iodide dissolves very easily in water. You put that in water, it's not going to just fall to the bottom and not do anything. That's what would happen. If you have a real big positive value for delta H of dissolving, then you just drop the solute in there and it goes down to the bottom and just sits there. Like calcium carbonate would be an example. Calcium carbonate, when you put it into water, it just falls down to the bottom. And you can watch it or swirl it or crush it up or whatever, it just sits there. But sodium iodide will dissolve because we can see it. Anybody have any questions about that? Pretty easy. Now, if you haven't taken the reading quiz yet, not the reading quiz, sorry, the review quiz, and you're still studying, you'll see questions that involve those kinds of topics. All right. So the next thing that we do, we move on now to covalent bonding. We're going to spend the rest of our time looking at the ins and outs of covalent bonding. The first thing that we have to be able to do is if we're given a chemical formula of a covalently bonded molecule, we have to be able to write its dot structure. Dot structures go everywhere in chemistry. Doesn't matter if you're just starting and learning about chemistry or if you're like in a degree in chemistry, or even if you're a PhD student or postdoctorate. Everybody in chemistry writes dot structures. We have to be able to do them. Now, dot structures are good for us to tell us what's bonded to what and how many, like if you have double bonds in there or all single bonds. So they're very helpful for us for representing molecules. However, one severe limitation that dot structures have, they don't give us any other information. Like they don't help us to know what the shape is. We have this thing called VSEPR theory.